Hi, everyone. Thank you for joining us in this Additive Talks session, during which we are going to learn more about the risks and challenges surrounding the use of AM in the nuclear industry. My name is Katie Sindri, Managing Editor at 3D Additive Media, and your host during session. I'll be accompanied in this virtual table by Iwan Gresh, our special guest who brings around this table competencies in additive manufacturing, corrosion, and nuclear. So Iwan will be my co-host. You can't see him, but you hear his voice. Hi, Iwan.
Hi everyone. Unfortunately, you can't see me on video, but I am here and I will be listening intently throughout and joining in when I can.
Thank you. Thank you. So around this virtual table, we also have two industry insiders, Benjamin and Yevgeny. So Benjamin, could you please tell us more about you?
Thanks. I'm Benjamin Betzler from Oak Ridge National Laboratory. Oak Ridge National Laboratory is a U.S. DOE Department of Energy contractor site. We are a lab for the Office of Science, and we do a lot of research and development associated with nuclear, manufacturing, biological sciences, and the whole nine yards. I'm here particularly because I'm a nuclear engineer who has been working with a lot of additive and advanced manufacturing technologies in a government type of reactor demonstration program. So essentially applying those technologies to reactor components.
Okay. Thanks, Ben. What about you, Yevgeny?
Hi everyone, Evgeny Brief. So I work for Burlock Technologies. We're a Canadian-based additive manufacturing company. So we provide components to a variety of customers from different sectors, primarily in the highly regulated ones, so space, aerospace, power generation, and so on. I'm a materials engineer by trade, doing metal additive manufacturing for the last 9 years. And coming from kind of looking at it from the supplier side, trying to see how we can supply critical components to our nuclear partners or energy generation and so on.
Yeah, thanks, Yevgeny. So, dear audience, dear professionals, as usual, make sure you write your questions in the Q&A chat. And at some point, during the conversation, we'll pause and let our panelists respond to them. Also, if you are working in a field related to the nuclear, I'm very curious to read your remarks, not only your questions on the topic. And so feel free to share anything that you have regarding this topic. So the topic itself raised, many questions within our team here at 3D Additive Media. So the conversation comes at a time when there are a lot of debate within political government and with regards to the environment. The nuclear, energy currently raises a lot of, debates, as I said. And my first question to you, Ben and Yevgeny, is really to know if you think this ambition of governments question the future of additive manufacturing technologies for this industry. So I will start with Ben.
Absolutely. So, additive manufacturing technologies and advanced manufacturing technologies are emerging, and they're rapidly developing, and there are going to be more and more components in general in all industries made through these processes. Particularly in post-industrialized nations like the United States, Canada, and a lot of Western European nations who are, at the forefront of a lot of the nuclear, technology, nuclear reactor type technologies. So it's going to happen. So in our implementation, what we focused on really is making sure we are prepared from a quality and regulatory level to understand what those technologies provide, what kind of benefits they provide, and understanding how they're different than conventionally made materials. In particular, I think they are uniquely enabling in advanced design, in particular applications for components that may not be available anymore. Because of supply chain issues, or because those components are just 40 years old and they haven't been made in a while. And also in refurbishment of existing parts, and that is kind of a newer technology that is being developed now. So I don't think it's about questioning, the future of those technologies. It's really about understanding, what those technologies provide, how you regulate them, and how well those components perform in these systems.
Well, thanks, Ben. What about you, Yavshini? Do you think AM can play, a key role in this energy transition?
Yeah, I'm sure it can. Just like it's playing a role in any other major industry, right? So it takes some time for the technical engineers and the designers to kind of start using the technology and understanding the benefits of it and kind of exploiting all the potential benefits it can bring to a sector.
Mhm.
We definitely see it in aerospace and space and power generation.
Mhm.
And we're gradually seeing more and more interest from the nuclear side as well.
Mhm.
Just like Benjamin mentioned, we have kind of two spokes. One of them is the new gen technology, SMRs or anything that has kind of the ability to explore the technology and design new products, but also sustainment and making sure that we have spare parts for older components that are not made anymore, or the supply chain is broken, or anything that we can help maintain existing nuclear power plants.
Yeah. Let's have a look at this technology standpoint. Renewable energy such as wind or solar power, is said to be similar to nuclear with regard to incorporating additive manufacturing. How do you think that's correct? First, and how, if yes? Jenny? Yeah.
I'm I'm not sure it is correct. Well, just from a point of complexity, right? So a nuclear power plant is significantly more complex, has
All right.
significantly more components in it. So significantly more potential applications for different types of parts, different materials that can be used versus wind or solar that are a bit more not simple, but in terms of the mechanical assembly itself, it's a simpler assembly and less parts involved. There are applications, but I don't see them to be as diverse as they are in a nuclear environment.
All right. Ben, do you think that's not correct as well?
I think it's correct in a certain way. What Yevgeny said about the complexity and the rigor for nuclear components is, bar none, very, very high,
Okay.
because you're irradiating, or you could be irradiating these materials depending on how close they are to your reactor, and that takes a long time to get data. However, I would say, the one unique capability of additive manufacturing in an advanced design process, so for new reactors like SMRs or new reactors like microreactors, the unique enabling capability of additive is rapid prototyping. And when
Okay.
you pull in additive as part of your design process, you have to pull in manufacturing engineers and you have to pull in mechanical engineers who know the additive processes, and you are making things.
All right.
That is very unique in an additive process, or with additive process, and it is uniquely enabling for design. So if we're talking about new renewable energy technologies that are undergoing that same type of process that can rapidly evolve, rapidly get to designs, get to workable, meaningful designs that are physical, that you could hold in your hand, that you could start doing prototyping with, I think that is a similarity. But that's for, again, advanced nuclear, new nuclear. We're talking microreactors, advanced reactors, SMRs, potentially small modular reactor components.
Well, good. We have two different, types of opinion on this question. Iwan, do you want to ask a question that will
Yeah,
add balance?
so there was one thing I was hoping to jump on there. So do both of you believe that additive manufacturing is most suited to SMRs and sort of developing new types of reactors, sort of whether it be molten salt or fluoride cooled high temperature reactors, rather than working on the traditional PWR, BWR, CANDU reactors that we currently have?
It's not that it's more suitable or not. I think it's an easier it's an easier path, just because when you start from a new application like SMRs, it's much easier to start from scratch and kind of incorporate additive in your design process, in your codification, in everything, kind of in the whole life cycle of the reactor, versus trying to find applications in a 40-year-old reactor that many times the parts, we can barely find drawings anymore, not to mention anything more than that, right? So I'm sure there's plenty of applications. It's just, but the nature of an existing nuclear reactor is it's resisting to change a little bit, if you can call it that way, right? So trying to find a pathway in and replace an existing component with an additive component is not straightforward.
All right. Yeah, that's something I usually hear. But I think that Ben, you want to add something.
Yeah. I'll give you an example. So most BWR and PWRs, boiling water reactors, pressurized water reactors, have fuel in tubes, right? Very long tubes. And what Yevgeny said is that those components are designed with manufacturing in mind, with a conventional manufacturing process. It's easy to make, or it's easy and known to make lots of very, very long tubes and then weld them in such a way that you do not get radionuclide release, right? It's a known process. You can do it very, very reliably, like absurdly reliably, as far as making sure those fuel tubes are sealed. So when you approach that with an additive technology, it makes no sense to print or use an advanced manufacturing process for a very, very long 12-foot few meter tube. It just doesn't. It's not cost effective, and the benefit there is there is really no benefit to that. So when we're talking about the application to newer reactor technologies, where you may be using newer materials, you may have different types of geometries. It's more applicable, and there is more benefit there. With existing nuclear reactors, we have an idea of where additive advanced manufacturing can be helpful, and it's with these components that essentially haven't been made in a long time. Imagine you're at a reactor plant and some component in the system breaks down. All right, now you have to figure out what that component looks like, what the requirements are for it. Do you have drawings for it? Are those drawings 40 years old? How do you get them to manufacturers so they can go make it, imagine in a beautiful scenario that you could take that part, you could scan it, you can load it into some software, you could take that and give it to a printer and then print that component and have that printer on site. There's benefit to that. We're not there yet, but that is the benefit or potential benefit for existing nuclear.
Let me ask a question that may help us have a better understanding of this concept, this context. Sorry. So, what are the requirements of a nuclear environment, Ben?
Yeah, so I think the unique requirements of nuclear is, if a component is inside the reactor core, is that it becomes irradiated. Okay. And I think that's unique regards to all the other potential applications in other highly regulated environments. And that's why I would say that the quality rigor level for nuclear is at the highest.
All right.
Not only does it have to perform from a thermostructural standpoint, at temperature, with temperature gradients, with flowing coolant, potential corrosion issues, but it also has to perform over a long timeline as it's being irradiated. If you want that part close to the core, and that irradiating materials takes time, and that is what one of the unique aspects of the nuclear environment.
All right, thanks. Okay, now from the manufacturing standpoint, of the topic, Yevgeny, so using AM usually requires to take into account several variables. So, do you think there's a specific additive manufacturing process that is more used or that is more compatible with this nuclear environment that Ben just described?
Yeah, I think it really depends on the kind of materials we're looking to print, and obviously the size of the components.
Okay.
So kind of the two that come to mind are laser powder bed or electron beam powder bed. So powder bed systems that can do the more smaller intricate components. So we're looking at turbines, looking at manifolds
Yeah.
of various levels of complexity. So those are really ideally situated for powder bed. Also, we have quite a selection of materials we can use, from the traditional steel grades to the nickel superalloys, so we can always tailor the material for the application.
Mm-hmm.
And for the larger elements, that will be direct energy deposition, whether that's wire or powder, because those systems can do a significantly larger scale components. Regarding criticality, yet to be seen in terms of whether they can perform in the same way as the components they replace. But definitely in terms of both repairs and in terms of just replacing large components, DEDs is the way to go.
Okay, thanks. Yeah, and speaking of materials, I usually hear that materials are mentioned as one of the key items that prevent engineers to achieve high performance products. Do we have the same issue here? What type of complexities materials raise in nuclear applications? What properties will engineer look for when choosing materials for these applications?
I would like to add something there, if that's okay,
Okay.
just to this question, is
Yeah.
to do with the state of the materials as they come out of the additive manufacturing process, and whether they require some sort of post-production treatments or surface treatments before they are finally ready to be involved in situ.
So materials usually dictated by the engineers. So a direct replacement is the easiest thing to do, right? So if the part is made out of stainless steel 316, for example, then offering the same product in the same alloy is the easiest way, instead of trying to requalify the same component using a different grade of material. But again, the requirements tend to come from the end user for us, because they'll still do the thermal simulation and all the mechanical analysis, and decide based on their own applications what's the best material for that. In terms of what we can do, that the kind of the palette of alloys we can print is growing, weekly, not daily. And more companies are offering more alloys in terms of powder form. So that's, while it used to be more of a limiting factor maybe 5 years ago, is not so much anymore. So it's fairly easy to find either an equivalent grade or a better grade to be used for that specific application. For Ivan's question, the vast majority of components will get post-processed one way or another. So heat treatment is the basic one. So everything gets heat treated, and then the heat treatment cycle is fine-tuned for the specific application, right? So we can always balance the properties. Heat treatment research is I would say a bit lagging for additive, because we're still relying on traditional heat treatment cycles designed for machined or cast parts, versus our starting point is very different. So there's still a bit of a gap to close there in terms of the best heat treatment for the additive components. But nevertheless, it's something that we do all the time for every component we print, pretty much, maybe with the exception of very basic prototypes, which somebody just want to see if it fits. And then surface finish, again, another application, really depending on requirements. If it's a fatigue, if it's a part that needs to withstand significant fatigue, then surface finish will be really critical. So you'll have various methods, both mechanical and chemical, to improve the surface finish. Machining is also something we do a lot of on critical surfaces, critical areas in the part. So yeah, the significant post-processing. So printing is only the first step of an additive journey, really.
Ivan, are you satisfied with this answer, this response?
Yes, I am. I was just sort of leading it into a lot of, when I speak to people, a lot of their ideas and their opinions are, we can 3D print this and we can throw it in and it's good to go. Whereas
Yeah.
I think it's important to think about the reality of the entire process of coming up with a design, building it, optimizing the build, and then also optimizing the heat treatment or the surface finish afterwards to ensure that it meets the requirements of the application.
Yeah. Yeah, Ben. You
Yeah,
wanted to say something? Yeah.
yeah.
Go
It's,
ahead. Go ahead.
it's certainly a challenge. Within the Transformational Challenge Reactor program, or the TCR program, in which we took additive technologies and tried to make parts and get them into reactors. We started that program 4 to 5 years ago, 4 years ago in earnest. And the technologies that were apparent to us at that time, technologies and materials, are not necessarily outdated, but there are better, newer technologies. So in particular, we looked at laser powder bed fusion. What was not apparent to us was e-beam powder bed, which would be better for the application. But laser powder bed fusion and some binder jet processes. So with nuclear reactors, the components in a nuclear reactor, they're mostly either metal or ceramic components, and ceramic 3D additive technologies are ongoing, really rapid development as well. The process, that I'll give you an example of is the TCR fuel form that we developed under that program. Again, over probably the course of 18 months to 2 years of fine-tuning a process to make this particular element. You can see that this element has a very complex geometry in it. The coolant channels that are running through this fuel form are essentially the art of the possible for that. This particular component, it is a binder jetted silicon carbide element. That element comes off of a printer. It's green. It will fall apart. You can crush it with your hand. What we do is we fill that part with fuel particles. This particular part has trizo surrogate particles in it. You fill it with fuel particles, you backfill that with silicon carbide, and then it goes through another process to densify this element so that it's hard and so that you get a solid radionuclide retention barrier in this component. What this is a very high density fuel form of a very robust ceramic material that is resistant to radionuclide release. So this is the type of kind of design process that you would go through, looking at what additive processes you have, how does that additive process fit into a broader context of a design process to get to a workable design that makes sense.
All right, thanks. Oh, gentlemen, let's pause for a minute because we have some questions that are, directly linked with some of the answer that you just shared. I would like you to respond to them in the Q&A chat. So our first question came from Bram. Sorry. Hi, Bram. What is the effect of new developments in the additive manufacturing field on its uses in nuclear? Think of the big advances made in AM of ceramics and upcoming multi-material printing. I don't know. Who wants to start with this one? Who feels comfortable with this question?
I can try anyway.
Yeah.
So again, as a company, as a company that makes components, we're always on the lookout for new technologies that can give us new tools to offer something different to our customers. There's a variety of technologies out there. There's always a new startup, something exciting happening, whether that's a new material or brand new technology, an improvement of a technology. That goes for ceramics as well, right? So it's all forms of binder jetting or stereolithography, and then the different companies take it into different ways. As an additive manufacturing enthusiast, I'm always keeping an eye on something that's happening. There's always a bit of a gap between a new technology and then its potential applications in industrial environments, right? So between launching a new technology and proving that it works, and then between having a demand for it from industrial users. So academy tends to be a bit more adventurous, but from an industrial user to use a new technology, there's always a bit of a gap. You need to prove that it's cost efficient, it provides an edge over something existing technology, and there's the investment that needs to happen. So
Right.
there's always a bit of at least a few years between something new and something that we can actually offer.
Okay. But just for, from my understanding, Yevgeny, even for, research purpose, have you already been, linked, or have you already had projects that are linked with multi-material printing?
We have had people asking about it.
Yeah. Okay.
Many people, yes. So we are. I'm keeping an eye on the likes
Okay.
of kerosene and then dual
Yeah.
materials. So the DD offers that fairly easily.
Mm-hmm.
The laser powder bed, what we specialize in, is a bit more tricky to do that with two materials. Again, not impossible. People are doing it as a startup. So again, we're keeping an eye on the demand. The interest is there. Let's put it like that. I don't know if there's a lot of demand. The interest is definitely there.
Okay. Okay. Ben, you want to say something? Yeah.
So if you simplify, the kind of flow chart of what types of materials to put into a nuclear reactor, you can do it like this. This is obviously oversimplification, but we're talking about temperature,
Yeah.
neutron irradiation or behavior with neutrons, and then the environment that it's in.
Okay.
Cooling. The majority of reactors in the world are water reactors, so that environment is a water environment with a water that is tuned to reduce corrosion, or in some cases a gaseous environment when that gas is inert. If you're looking at advanced reactors go beyond what is currently used and challenges it two ways. It's new material or new environments that can corrode materials in different ways. And then it is even higher temperatures and potentially higher neutron irradiation behavior. So, as far as multi-material printing, there's a lot of interest in that because some of these higher temperature coolants, for example, like a halide salt, like a molten halide salt, are corrosive to certain materials. So as far as multi-material, you're talking about, hey, can you get a base material that would structurally perform, like a stainless steel, and then coat that material in some way, or build a gradient to a different material that is known to be corrosion resistant, right? Because those are often two separate materials, right?
Mm-hmm.
Or in molten salt environments, in certain environments, certain types of materials are far more corrosion resistant than others, but those materials aren't necessarily great for pressurized boundaries or for building really large components, or they're potentially expensive.
Okay.
So there's a lot of applications there. As far as ceramics go, most of the ceramics I see in nuclear applications, it's all about that density, getting very dense components, and that's a challenge with additive processes.
Okay.
I would like to chime in there if possible. I think that that really leads into the next question to do with surface finish, because I'm very aware of dealing with corrosion, especially when you're thinking of a molten salt reactor. The idea of putting something extremely corrosive and heating it up, and then pumping it through something with a relatively rough surface is sort of asking for corrosion issues. I just thought they would lead well into the next question of, do you consider mitigation of crud deposition to be an issue given the relative roughness of the parts? I think it was interesting that you brought corrosion and surface roughness into that, Benjamin, sort of feeds into this next question.
Yeah, absolutely. I have a number of components on my desk here, and if you're here and you're feeling them, this is a stainless steel component. This is essentially art of the possible. You have heat transfer or fitment elements here. You have conformal cooling channels on the end here around a potential complex shape. There's a lot of pieces in here for heat transfer or enhancing heat transfer and other elements. if you were holding these parts, you'd realize that they're rough. I don't know if you could hear them rub against my hands. They're not.
Yeah.
This is laser powder bed fusion. I have some others here on DED systems. But yeah, that is a major concern. Particularly crud deposition, which has been observed on a number of reactors. It's not really well predicted. It is known how it occurs on pressurized water reactor. On pressurized water reactor assemblies, but predicting that is difficult. So, if you're wanting to use these types of materials in these applications, certainly experience from testing is really critical. And again, that kind of feeds into my comment on the QR or the quality rigor level on nuclear is very, very high, and it takes a long time to get sufficient data on these components. But yeah, these are rough. I feel like in most additive applications in a lot of industries, you would finish a surface if it needs to be finished, if it has a functional need to be finished. Otherwise, you wouldn't want to finish it. If you have components in a nuclear reactor that are in a coolant area, and they essentially have or coolant bypasses them, then you're worried about two things about that surface roughness: corrosion, enhanced corrosion, and then also any type of thermofluidic behavior that would induce, like additional pressure drop, for example, because these components could be particularly rough.
And I think that for the first time during since the beginning of this conversation, Yevgeny, agreed with you on some of the things that you just said.
I completely agree. I think Benjamin is right on spot there. We tend to finish the surfaces that need to be finished, based on the application, right? If the application requires a full surface, to be finished, then that's the way it has to be done. Yeah. What's the best way of doing it? That still has to be decided, right? As I said, there are chemical approaches, mechanical, so polishing. Different alloys behave differently and kind of more susceptible to different methods as well. But yeah, critical surfaces are critical, so they have to be treated that way.
Yeah. My next question will be to know the different, nuclear industries and regulatory bodies that can support codification and industrialization of additive manufacturing in this field. I don't know if Ben wants to go ahead with this one.
Absolutely. So, within the Transformational Challenge Reactor program, we were essentially wanting to demonstrate a nuclear reactor. So we wanted to get components in an operating nuclear reactor and do all the technical or meet all the technical requirements for that. If you want to do that on a short time frame, you have to accept a few lower kind of, baby steps, essentially. Okay. Low dose, low source term, more mitigable temperatures. So as far as the materials that we got, we put them into reactors and irradiated them to essentially a dose or neutron fluence level that would encompass our demonstration. Okay, so the key was, hey, let's limit this demonstration timeline or the reactor operation timeline so that we can actually irradiate all the materials we need to irradiate beforehand, so we understand their behavior up to that limit, right? As part of that whole process, we engaged the Nuclear Regulatory Commission and the Department of Energy. If we were to deploy the reactor in the way that we wanted to, the Department of Energy would be our regulator. So the Nuclear Regulatory Commission, the United States Nuclear Regulatory Commission, would not be our regulator. However, we engaged the NRC very early on in the program and invited them out to Oak Ridge to essentially sit with us as we do the design and build process. These manufacturing processes are new. They're not conventional processes. They're not familiar, and in a lot of ways, there's not, a standard for applying that process to a nuclear component. However, the Nuclear Regulatory Commission was very, very open in trying to understand those technologies, because either we convinced them or they were convinced themselves that, again, you're going to see more and more advanced manufactured parts in nuclear reactors in these highly regulated environments, because that's where the industry is going. That's where there is commercial arguments to do that, or economic arguments to do that. And that's what they're going to see. So they are preparing rapidly. They term it as components made from advanced manufacturing technologies. So they encompass additive as part of that. Also some other novel technologies that could be counted as additive. And they're very rapidly essentially developing a process to understand and essentially review these components that are made from these technologies. One of the challenges there is that, like Yevgeny said, stuff changes all the time. And what the NRC did here in the US is they made a list 3 or 4, maybe even 5 years ago.
Yeah.
And that list, includes things like DED, direct energy deposition, laser powder bed fusion, cold spray, some other technologies that may or may not be the highest technologies of today. But in any case, they are rapidly developing processes, and we have within this program put parts in NRC regulated reactors. So they do have a process under which you can go and you can say, hey, here's an additively manufactured component. It has these performance requirements. We built it in this way. We've tested parts, witness specimens with those builds. They operate as expected. We can put these in a reactor. So they are not allergic to, at least in the United States, the regulator is not allergic to these components, because, again, I'm sure they understand that there's going to be more of these coming to them.
Yeah. I know you were talking, with an experience, that is highly linked to the US environment. And I also know some professionals in our audience are based in Europe. So I wanted to know if, we have the same environment in Europe as well. I don't know if Yevgeny has any experience, on the European market of this sector of activity, or even if Iwan wants to add something, or the audience, please feel free. If you have any remarks regarding, the regulatory environment in Europe, please feel free to share so that we can learn from each other.
Yeah, so one thing, in Europe, as far as I know, it's done by a country basis, in that the UK is different to France, which is different to Poland, which is different to Lithuania, etc. And I think that to integrate additively manufactured parts into the nuclear supply chain, one thing that needs to be done is a standardization of tests. So we can compare parts built in the same material, using the same method, with the same surface finish, in the same environments. And I feel like that sort of standardization and testing criteria is going to be critical if additive manufacturing is going to be introduced into the supply chain, even more with small modular reactors. The general thought being, if you build 100 of something the same way, by the time you get to the 50th and the 60th one, you've learned lessons along the way, and you can build them more efficiently.
All right.
That's my thought.
All right, thanks, Iwan. Yevgeny, do you want to add something?
Yeah, I guess just to add to Ivan's comment, that's absolutely, from our point of view as a supplier, that makes everything much more complicated, right? Because we have to live by different rules.
Yes.
So depending where the customer is located, they have their own set of regulations that they have to follow, right? And we have to kind of play by different rules every single time. So it makes it difficult to establish the process, because every time the process is different.
Yes.
So yeah, we're all eager to have standard set of requirements.
Mm-hmm.
So the SME started with the additive manufacturing codification standard, and then saying pretty much you just follow the code and lower the temperature.
Yes.
But once we have something standard globally, or at least across several leading nations, I would say,
Yes.
it will make it much easier for companies like Burloak to support the end users who are supplying those components, right? Because
Yes.
getting the same component qualified 10 different times, the different campaigns is challenging.
Yeah. And this question from Philip Oris is quite dumbly in the Q&A chat. Philip said, we are a manufacturer of LPBF machines. We don't make products. What will be the best way to develop technology partnerships in this field? So I know ORML and Biolog, I mean, you guys, I mean, your company, your respective company have, I mean, their own way of developing partnerships. I don't know if you want to share any resources with Philip. Yeah, Ben?
Yeah, so as a U.S. DOE federal contractor, we have a facility here called the Manufacturing Demonstration Facility, which is very much focused on industrial partnerships, essentially helping industry partners come in, fine-tune processes, procedures that will deliver the parts that they need for the performance that they need. And then provide that essentially recipe to those partnerships. So there's a number of different ways that U.S. companies can engage with a site like Oak Ridge National Laboratory to help kind of develop the procedures for the applications that they see most fit.
All right, thanks, Ben. Yevgeny, do you want to say something about that?
It really depends. So it's case by case. So we do partner with various companies along the way. Each company kind of brings its own expertise to the table, right? So whether that's materials development or testing capability or anything really that's that adds value to the overall proposition. So that there's no really, because we're a private company, so there's no really one
There's
way
no one-size-fits-all.
of doing it. Yes, it really depends
Yes.
what we're talking about.
All right, great. Iwan, my co-host, we're looking for, I'm just checking if you have any questions before I move forward to mine.
Nothing sort of particular that points out. I would like to highlight, although we mentioned sort of the ability of small modular reactors and how it's good to repeatedly build things the same way, I would like to point out there is obviously a key fault wherein if you build 100 reactors the same way and then there's an intrinsic fault in those reactors, then they're all sort of need modification then. So there are definitely opportunities and also challenges. So there are pros and cons to do with standardization, particularly as we move into small modular reactors.
Yeah, I feel like certain events in the nuclear industry have obviously caused these ripple effects, right? An accident happens halfway across the world in Japan, and now every single reactor in the United States is prepared for a similar event, and they have to be prepared for that event, regardless of its probability. It's just not going to happen here, and I would say that there's a flip side to that. If you don't have standardization, for example, in the United States, all the reactors are different. The implementation of the corrections for an event like Fukushima has to be different, or inherently a little different at each site. Regardless of that, again, every U.S. reactor is prepared for that type of an event, such that you do not have a radionuclide release. So maybe it makes it a little more simpler when you have several. You can push an update, locate the critical part or the critical component. But yeah, I think that's a really valid point, because these SMRs, they'll be new. There are several that use water technologies that are more familiar, but they will still be new, and there will be new things about them that you can only find out through a lot of operating experience, of which, the light water reactor community has 50 years of operating experience in that environment, at those temperatures, at those radiation conditions, with that coolant.
Explain. Yevgeny, do you want to share something?
No. I think Ivan and Benjamin covered it. I guess the hope is that once you build one or two and kind of prototype it and run it for a few years until you start making more of them,
Yeah.
some experience and identify at least the major issues, because I'm sure there'll be issues. Like Benjamin said, it's a brand new design. There's no experience with it. The environment is more extreme than potentially existing reactors.
Mm-hmm.
So I'm sure there'll be issues. Hopefully they'll be rectified before start mass production of SMRs.
Mass production is very far away from us right now. Okay. Do you have any concluding thought? Any last words that you would like to share regarding these insights? We no longer have any questions from the audience. I really hope the panel has been useful for all of us. So for all of us, and for all of you who are listening to us. So, any concluding thoughts regarding the panel, regarding the potential risks and challenges we should be aware of regarding the use of AM in the nuclear industry? Ben, do you want to start?
Sure. First I'll echo a comment I've said already. There's no there's no reality where there are going to be additively manufactured components in nuclear reactors in the future. It's going to happen. Advanced manufacturing technologies check a lot of boxes for more economical deployments of reactors, of components in reactors. So it's coming, and the challenge is to be prepared for it and to essentially, see what that penetration is. How far does that go? And that really goes back to, what are the limits of the technologies, what types of materials you can build, and essentially how much testing you have to do for the parts. There's one key component of these processes that are unique relative to conventional processes, and that is the manufacturing process for additive components is very data rich.
Mm-hmm.
A lot of data from those prints. There's all the metadata from the machines themselves. You can instrument the machines to understand essentially temperatures, temperature behavior, cooling behavior as you're going through those build technologies. You can essentially build what we would call a digital thread for that component. Essentially, it is all the associated data that component saw during its manufacturing process, including when it was cut, the heat treatments, where it was machined, how it was machined, to essentially deployment. And all that digital data can be used to tell or predict certain characteristics about that part, including potential failure modes of that part.
Okay.
They can do it. You can predict it. The question is, can you predict it well enough such that a regulator would be confident in you using that data to tell you something about that part, something very firm and specific about that part. And that's a lot of where this digital thread, digital factory, these types of terminologies come into these particular manufacturing processes. And it's what can really supercharge them and make them more ubiquitous in a lot of different environments for a lot of different parts.
Thanks, Ben. Before I give the floor to Yevgeny, I wanted to ask just in case, if you have any questions, Ben, do you have any questions for Yevgeny? Yeah, we never know. No?
My only question is what part is next up in a reactor in Canada or in the US, do you think?
I think it will be baby steps, really. I think we'll start with parts that don't really see radiation. That's my assumption, right? We'll start with the ones that the turbines and all the semi-critical, let's call them, right? Well known, but not prone to radiation exposure. And then we'll make our way from there to more critical part as the kind of the regulation is in place. So you said, the US may be probably a bit ahead of the regulation. Canada is again working on it, but until we have it, I don't think that the nuclear operators will be comfortable in deploying components in the radiation environment. That's one, and also we're looking at, there's interest in replacing old obsolete components, right? But then the problem is that at least we've encountered so far is that there are no spares available to scan. There are no drawings. There are no models, obviously. So you'd say that the magical thing, we'll take one, we'll 3D scan it, we'll have a model, but there are none. So the only ones we have are installed, and then we need to wait for a shutdown to get someone inside and scan it. It becomes, it's difficult, right? So it's definitely a demand. There's definitely a need for it, but the kind of how to do it exactly, we're still trying to work it out. So I think it will be like two ways. Yeah, supply new components for non-critical applications first, and then gradually replacing components that you just don't have a choice, and you have to print because there's no other way to make it at the moment. And then we'll make our way to more critical areas as the industry kind of a bit more comfortable. And we've seen the same with, I know it's not the same, but we've seen the same trend with aerospace, for example. You start with low criticality components, and you gradually make your way up to, turbine blades and new engines, right? Rotating components, the most critical part in there. So, people fly now on the new Gen X G engines, they have printed blades, right? So whether they know it or not. It's getting there, but yeah, there's a technical challenge, there's a regulatory challenge, there's a psychological barrier that needs to be passed as well, right? For a lot of the maybe the older generation of designers, kind of maybe not used to it, not comfortable, not confident that the AM parts could perform the same way as traditional parts.
Good response. So what are your key takeaways?
Again, we're keen to work with a lot of end users. Nuclear is exciting for us because at the core we are a bunch of materials people, so it's exciting for us to solve challenging problems from a materials point of view, from a performance point of view. We're always keen to kind of try and develop a long-term relationship with the end user, trying to understand the application, trying to understand the risk, trying to understand how we can, add our experience and maybe simplify something or add value to a component. But yeah, we're always keen to hear from from the customers really, because they're driving the need for component A or B.
Yeah, thanks. And just in case, do you have any questions for Ben?
No, I've been following the Oak Ridge work on nuclear. It's always exciting. We're learning a lot from it as well. So, yeah.
All right. Iwan, do you want to share some concluding thoughts or some
so there's one sort of thing which we haven't spoke about much and is often a topic in the nuclear industry, is to do with spent fuel storage. And I feel like one opportunity that additive manufacturing has is to build materials with built-in sensors to help aid with spent fuel storage. And I feel like it's important not to just look at things from a in-reactor point of view, but to look at the whole life cycle. So think about how additive manufacturing can help from the mining of uranium up to the processing plant, up to the reactors, up to the post-reactor spent fuel storage site. I just wondered if either of you had any thoughts on that.
All right. Thanks, Iwan.
Yeah, I think there's a huge opportunity there. As part of, again, the TCR program, we studied how to leverage these processes for new novel concepts and understanding more about systems. Embedded sensors was one of them. So For example, here this is a consolidated metal part that we've printed on a powder bed fusion system. You can see that this design has likely several different kind of functions. It's a coolant kind of directing function. It's a support function. It would be welded to a conventional tube. And then this is the same component, but with some embedded sensor ports on the sides here. We've worked a lot with embedded sensors. It is a challenge to embed sensors in these processes. Powder bed processes, you have to stop and then restart prints, which are not super
not ideal, is it?
For the silicon carbide components, the processes that these go through, they're high temperature processes, so that sensor better survive 1,000 degrees C in a very corrosive environment as you're densifying this material. We've successfully embedded sensors in silicon carbide as well as metal components, but your point is very valid. That whole life cycle, reprocessing facilities, for example, can you embed sensors in critical locations? And the answer is yes, and you can do it in a lot of different materials. And a lot of what the work goes on in DED in a number of different areas is embedding, or functionally, what would be equivalent to embedding some sort of channel for cooling, like conformal cooling and tooling, or for sensing. So it's definitely a huge opportunity to allow us to understand more about these systems. But it is an in-kind challenge to make sure those sensors survive, as well as deliver the data that you want them to deliver.
Yep, Jenny, do you have any thoughts to share regarding this?
Yeah, as Benjamin said, sensors is a challenge. It's not the process that we use, especially powder bed, are not designed for adding extra things during the process, right? Quite the opposite, designed to keep the chamber as clean as possible. But I think DED will be a good option for that because it allows a bit more flexibility. And also, yeah, I agree that you have to look at it from the whole life cycle, right? So mining is a bit easier because mining is mining.
Yeah.
So from the difficulty point of view, it's a bit easier just because it's a known process. The ore is different, but the process is similar. But in encapsulation, I'm sure kind of additive of ceramics still has a lot of potential there in terms of both ceramics and glass for encapsulation and for storage. And I know a lot of people working on it, so I'm sure there's a lot of potential in that field. Yeah, it's definitely a challenge.
Thanks, Yevgeny. Well, on these good notes, gentlemen, this is it. I think that we have embraced all of the main points of these topics, and I'm very glad you joined us for this conversation. I'm very happy for the, significant, very important questions that the audience shared today. Please feel free to always send us your feedback regarding our Additive Talk session, regarding the main topics that you would like us to address during such type of conversations with industry insiders. And feel free to share any thoughts regarding this important topic regarding AM in the nuclear industry. Let me hold. Yeah, I think that we have. Yeah. Thanks, Gabriel. I thought that it was a question. So Gabriel is thank you. Yeah, is thanking us for the interesting conversation, and yes, and also stay tuned for the next Additive Talk session that will be announced soon. Thank you very much, gentlemen, for taking the time to share your resources with us. On these good notes, I would like to wish you a very good end of day and or good evening or wherever you are in the world. Thank you very much. Thanks, Iwan, for co-hosting this panel with me.
You're welcome. I've had a great time. I've thoroughly enjoyed.
It's a pleasure. Have a nice day and nice evening. Thanks.
Thank you very much for the invite.
Yes.
Thanks, y'all.
Yeah.
Bye bye.